this. Yeah? So we just copy paste the formulas into each cell and modify the command slightly to locate the correct cell in the formula, and then you get these values. Okay. So for each sample, we calculate their X bar and standard deviation, right? And given with the expressions in the slide, we'll be able to create a confidence interval. Okay, we find the LC or lower limit and upper limit, right? And we create a confidence interval. Right, for the last line, last row, okay, you will see if it's either greater, well, we capture the value of 35. If 350 is within the range of your confidence interval, right? So this is blank 1, and we create the 0, 1. Okay, 1 means yes, 0 means no. Okay, and basically we can apply this. Okay, we just use if-then command to create these yes or no values, and we just multiply them to get 1. Okay, if both conditions satisfy, then we will have the value of 1. If either of them become 0, then we will have the value of 0. Okay, so this is the way to create this. And we can also use the color coding, okay, to create the value for us to see. If the value is 0, it will show up to let us know that these two samples, they gave us the confidence interval that do not capture, do not include the population mean of 350. Okay? So for this one, you can see that, right, the lower confidence limit is 352. It's even higher than the unknown population mean 350. So it doesn't cover the mu, right? And for the sample number 13, the upper confidence limit 346 is still smaller than 350, so it does not cover the population mean. Okay, so it shows that, okay, for each confidence interval calculated from each sample, it will either yes or no cover or not cover the population mean. Okay, so there is no issue of probability, but it's the issue of proportion. Okay, so I would like to show you if we can play these kind of, well, random samples for several times. So how we get these values. Okay, so this sheet, okay, in your exercise, you got the fixed number, right? But in random number sheet, I create a random generated values. Okay, so let's look at the final column. I will randomly run this experiment so that you will see how it runs. Okay, if I press F9, you will see that it changes. Have you seen it? Yeah. So I press F9, every values on top will sample again. Okay. Right, if I keep pressing it, you'll find the values changing. So you will see some sporadic red cells on the bottom row, right? It shows 0. So it means that in this trial, okay, on the screen now, there are 3 confidence intervals that do not cover the value of 350. Okay, so it means that I have 20 samples. 3 of them are do not cover the 350. So that's the issue of proportion. So if I keep pressing this, in the long run, roughly 5% of these intervals, 5% of interval will not cover 350.
Wait, so what did you, sorry, I didn't get it. What did you press to make a change?
F9. Well, this is my file. You don't have it. Yeah, well, this is just a demo to show you that the meaning of long run keep creating, because each sample I will give you create a confidence interval, right? So it means that, well, usually we don't have such luxury to have so many samples. We have only one sample. Okay, we have only one sample, then we can calculate only one confidence interval. Okay, but since now we got this kind of idea in mind, we know the exact property of such confidence intervals. So now we have a correct interpretations of the confidence, the alpha, confidence level 1 minus alpha, and the proportions of the meaning of the confidence interval. Okay, it's not probability, it's proportion. Okay, so you've got the feeling now. Right, so this is the extended example 10.1. Proportion. In this case, I have 20 samples here, and 4 of them create confidence interval that do not cover the population mean. So in this case, I have 4 over 20 is 20%. Yeah. So if I keep running this, then the proportion of such red cells from here will be roughly 5%. Yeah. Okay. Right. So I hope you because confidence interval is has a very important implication and it plays a very important role in statistics. And if we have incorrect understanding, then we will make wrong judgment and wrong decisions. Okay, and let's talk more about the interval width. So the wider the interval provides less information, yeah, because we have no confidence in concentrating. So the width of the confidence interval estimate is a function of 3 things: confidence level, which is alpha, and the population standard deviation, which is sigma, and the sample size, which is n. Okay, so again, I use the colors to denote the positions of these 3 items. So if the confidence level is larger, if the alpha is bigger, okay, if the alpha is bigger, or the larger values of sigma produce wider confidence interval. Okay, so as we listed here, if the alpha to be smaller to the either 2 ends, right? Alpha is smaller, then 1 minus alpha is bigger. 1 minus alpha is bigger, and we will have a larger values of z. So it will make the interval, the width of the interval wider. Okay? And for the red population standard deviation, because it's on position of numerator, so if it's bigger, then the width is wider. Okay? And the sample size, okay, increasing the sample size will decrease the width of confidence interval, okay, while the confidence level can remain unchanged. But with more sample size, well, it means that you need more resource or more time, more money. The cost of your obtaining the sample will increase. Okay? Either you have to wait longer, you have to spend more money to buy the sample, or you need some more people to help you collect the data and things like that. So the cost will be higher. Okay, so there must be some trade-off. Okay, and some people were asking why we have a square root of n underneath sigma in this expression. Okay, this is because we are talking about sampling distributions, particularly for the sample mean. Okay, And imagine or try to recall that example, first one and second one, we throw the dice. 1 die, 2 dice, 3 dice. Right. The mean, the X bar, okay, the possible values, the range of the possible values will increase, okay, but the centrality will converge, okay. So you will try to, you can imagine that with the n increases, the triangle or mountain-shaped distribution will tend to be normal. Okay, so that is the central limit theorem. And to measure the centrality, we have to take into account the number of samples, the n. Okay, because the n will, the effect of the n, the impact of n is to make this distribution like normal, tend to be normal, approximately normal. Okay, and the statisticians have developed some kind of mathematical deductions to put it a square root of n so that the speed of convergence will follow this structure. Okay, so the square root of n here is for sampling distribution, and try to understand the behavior of the X bar. Okay, so that completes our first section for statistical inference, the estimation part. We have point estimate, quite straightforward, and use these ideas, we create interval estimate, and we call it confidence interval. Okay? And it's called confidence because we have the value of alpha. Okay? And alpha is the probability that we hope that we won't, that we allow the probability that we won't get the correct unknown population mean. Okay? And we keep running this, and we can create the proportion to capture the mean. So this is the estimation. Right, so let's move on to the second part of the statistical inference, which is hypothesis testing. Okay, it's built on the idea of estimation. So the hypothesis testing is the second form of statistical inference and has a greater applicability. To understand the concepts, we start an example of non-statistical hypothesis testing. Okay, it applies a lot as well. Actually, we have this kind of logical thinking within our mind, and we apply it daily. So a non-statistical hypothesis testing, okay, a criminal trial is an example for this one, without using statistics. Okay, well, it's quite shocked to learn that law school students in Taiwan do not learn statistics. Every single law student in Taiwan, they never learn statistics. They have this kind of idea, but they won't study it or analyze it using statistics. It's a huge shock for me because no wonder there are lots of interesting cases in Taiwan. But anyway, so this is a non-statistical hypothesis using the criminal trial case. Okay, in a trial, a jury must decide between two hypotheses. The null hypothesis is for the H0, the defendant is innocent. And we have a second hypothesis called alternative hypothesis, H1, okay, the defendant is guilty. So basically, we have two hypotheses in a hypothesis setting, okay, H0 and H1. And H0 is called null hypothesis, and H1 is called alternative hypothesis. So the jury does not know which hypothesis to choose, so they must make a decision on the basis of evidence presented. Right? Well, everyone knows this. So in the language of statistics, convicting the defendant is called rejecting the null hypothesis in favor of the alternative hypothesis. Okay, we reject the null hypothesis. It means that we don't think that the defendant is innocent, and in favor of the alternative hypothesis, it means that we think the defendant is guilty. Okay, so that is the jury is saying that there is enough evidence to conclude that the defendant is guilty, or there is enough evidence to support the alternative hypothesis. Okay, so this is one possible outcome. The other possible outcome is that the jury acquits, is saying that there is not enough evidence to support the alternative hypothesis. Okay, notice that the jury is not saying the defendant is innocent. No. They only say there is not enough evidence to support the alternative hypothesis. Okay, well, this is the statistic language. Okay, so statisticians will never say we accept the null hypothesis. We will never say we support the null hypothesis. Okay, perhaps in plain language, in daily conversations, you will say, oh, we accept the hypothesis. But in statistical settings, statisticians will never say such words. We accept the null hypothesis. No, we will say we have no evidence to reject or to support the alternative hypothesis. Okay, statisticians are usually very conservative. Okay, they say things based on evidence and also statistical reasoning. Okay, so given this structure, there are two possible errors. Type 1 error occurs when we reject a true null hypothesis. So null hypothesis is correct, but we reject it. Okay? So the type 1 error occurs when the jury convicts an innocent person. So this is wrong. Okay, this is wrong case, possible errors. And the second type, called type 2 error, occurs when we don't reject a false null hypothesis. Okay, the null hypothesis is incorrect, but we do not reject it. Okay, notice I didn't use accept, we said we do not reject. So when a guilty defendant is acquitted, okay, it means that we make a mistake as well. Okay, so this is a type 2 error. Okay, so we have corresponding words for these two errors in Chinese, right? Okay, so the probability of a type 1 error is denoted as alpha, and the probability of a type 2 error is denoted as beta. Okay, and these two alpha and beta are inversely related. Decreasing one will cause the other one to increase. Okay, and you might think, well, there's an alpha again. In fact, this alpha is the same with the previous alpha. Okay. We have different names here. We have different interpretations here, but the underlying structure, underlying assumptions are the same, given the same alpha. So alpha plays a role of type 1 error here, and it plays the confidence level in the estimation part we just learned. Okay. So for non-statistical hypothesis testing, in the judicial system, type 1 error are regarded as more serious, which is type 1 error. In other words, we reject a null hypothesis. Okay, we convict an innocent person. This is more serious than the second type. Okay, we try to avoid convicting innocent people, so we are more willing to acquit guilty people. Okay, so type 1, type 2 error. So in statistics or in judicial system, we prefer to control alpha. Okay, we try to keep alpha small because type 1 error is more serious than type 2 error. So either in statistics or judicial system, we will have this kind of similar mindset. So we arrange to make alpha small by requiring the prosecution to prove its case and instructing the jury to find the defendant guilty only if there is evidence beyond a reasonable doubt. Enough evidence. Okay? Right, so given this non-statistical hypothesis testing, we all understand what happens in the judicial system, then let's try to summarize this. Some critical concept here. First, there are two hypotheses, null hypothesis and alternative hypothesis, H0 and H1. And the process begins with assumption that the null hypothesis is true. So we always assume H0 is true. Okay, so this is the fundamental beginning, starting point of a hypothesis testing. We set up null hypothesis and alternative hypothesis, and we assume null hypothesis is true. And the goal is to determine whether there is enough evidence to infer that the alternative hypothesis is true instead. Okay, so it means that we hope that we can collect sufficient evidence to reject null hypothesis. Okay, so in this case, H0 and H1, which one is more important to us? H1, alternative hypothesis, because we are collecting, we intend purposely to collect data aiming to reject the null hypothesis. It means that we hope that the alternative hypothesis is true. So alternative hypothesis, it means more. It's more important to us, so that we hope we can reject H0. Okay? So this is the underlying rationale behind this statistical hypothesis testing. Okay, we have two hypotheses, and because we have only enough evidence or not enough evidence to reject null hypothesis. Okay, so in this case, H1 is more important than H0 for us. Okay, because if we can reject, then we can confidently say that H1 is actually true. Okay. Right, so two possible consequences conclude that there is enough evidence to support the alternative hypothesis, or there is not enough evidence to support the alternative hypothesis. Okay, and the last concept, the two possible errors of type 1 error, type 2 error. So type 1 error is to reject a true null hypothesis, and type 2 error is to do not reject a false null hypothesis. Okay? And probability of type 1 is alpha, probability of type 2 error is beta. Okay, so these are the non-statistical hypothesis testing settings. We got these structures. And we can apply this concept to statistical hypothesis testing. Okay? So similarly, two hypotheses, null and alternative. And since now we are talking about statistics, so the null hypothesis, H0, will always state that the parameter equals the value specified in the alternative hypothesis, which is H1. Okay, because we are talking about statistics, so we must have some numbers, some numerical values. Okay, and these numerical values will definitely appear in H0 and H1. And typically we will set equal in the equality in the null hypothesis. We'll say H0 will be something equal to a specific value. Okay? Right, so consider example 10.1, just play with. Rather than estimate the mean demand, the operations manager wants to know whether the mean is different from 350 units. Okay? We have done the point estimate and interval estimate, right? And the operational manager wants to one step further. If the mean different from 350. So we can rephrase this request into a test of hypothesis. So H0 to be mu equals to 350, and H1 is mu does not equal 350. Okay? A very straightforward setting. H0 and H1. And two hypotheses, what's the next step? Is to start with the null hypothesis 2. Okay, so the testing procedure begins with the assumption that the null hypothesis is true. So we assume that, well, mu equals 350 is true. It's true. And then we collect data, right? And we try to calculate all these things we just discussed. So the goal of the process is to determine whether there is enough evidence to infer that alternative hypothesis is true. The same structure of the statistical one. So again, two possible outcomes. conclude that there is enough evidence to support the alternative hypothesis, or we say we reject the null hypothesis. We in favor of the alternative hypothesis. So this is the first possible outcome. And the second one is to say that there is not enough evidence to support the alternative hypothesis. So we are not rejecting. We cannot reject the null hypothesis. Okay? We cannot reject. Okay, again, we never say we accept. We won't say we accept. We just say we not rejecting. Right. So once the null hypothesis and alternative hypothesis are stated, the next step is to randomly sample the population and calculate a test statistics. Okay, so in this case it's X bar, the simple mean. So if the test statistics value is inconsistent with the null hypothesis, we will reject. Okay? But the thing is, what does it mean by inconsistent? So for a little example, suppose that we are trying to decide whether the mean is not equal to 350. Okay, so a large value of X bar, for instance, say 600. 600 is much larger than 350, right? So we may be quite confident saying that, well, the mu does not equal to 350 because our sample creates a value of 600. Okay, but if the X bar to be 355, just 5 more above 350, then we may not be so confident saying that, well, the mu, the X bar may be close. So 350 could be correct, possibly. Okay. So, but how about 370, 380, 400? Okay. So, how do we develop such confidence and to make the decision yes or no? Is the mu equals to 350? Okay. So the concept, again, we have the two types of error. We hope that we can reduce both alpha and beta, but it's not. It's very difficult for us to make these two goals simultaneously because there will be inverse relationship between these two. And alpha is called significant stable, so it's the same here. Okay, so the non-statistical hypothesis testing gives us the basic concepts, and we apply that into statistical setting. It's the same, but the thing is that we have to plug into the numerical values in the statistical hypothesis testing things. And the null hypothesis will be the, say, parameters, population parameters equal some specific values, as we've seen here, like this. Okay, so this is the first step of setting a hypothesis testing question. Right, so let's quickly look at an example. So the manager of a department store is thinking about establishing a new billing system for the store's customers. So she determines that the new system will be cost effective only if the mean monthly account is more than $170. So a random sample of 400 monthly account is drawn, and for which the sample mean is 178. Okay, so the manager knows that the accounts are approximately normally distributed with a standard deviation of $65. So can the manager conclude from this that the new system will be cost effective? Okay, she understands that the system will be cost effective if the mean will greater than more than 170, and he got a sample of 178. So can this sample answer her question? So how do we proceed? The system will cost effective if the mean account balance for all customers is greater than 170. So we express this belief as our, research hypothesis, alternative hypothesis. So let me modify it directly. So this is another alternative hypothesis. Okay? So H1 is mu greater than 170. This is something that we prefer to be true. We prefer to be true, right? So given this, the null hypothesis will be mu equal to 170. another process. Okay, so they specify a single value for a parameter of interest. Okay, so this is something